So in the last few sections, we've demonstrated that a system which needs to learn a complex combination of behaviours will tend to be constrained into this general architectural form. Two subsystems, one detects receptive fields, the other interprets each current receptive field detection as a range of recommendations in favour of a range of different behaviours. We also talked about a number of different types of behaviour that could be recommended, and I'd like to summarise the different types. There can be behaviours directed towards the external environment of the system, but also behaviours directed back onto the system itself. First, let's think about the major types of externally directed behaviours for a brain. To make it a bit more specific, let's think about behaviours in response to perceiving a cat. Suppose you're out for a walk with someone and you see a cat. There's a number of possible external behaviours. You could stroke the cat, which is a motor sequence behaviour. You could say, "There's a cat," a speech behaviour, but involving motor movements of the mouth, the tongue and the throat. Or you could study the cat to understand its body language. Notice whether it's purring. In other words, you could select attention behaviours. And these attention behaviours could again involve motor movements like shifting your eye gaze to different parts of its body. Or you could continue your walk, ignoring the cat. Some of the alternative behaviours are incompatible. You can't both stroke the cat and walk away from it. These alternatives may all be recommended, but only one can be chosen. So any one receptive field detected within the perception of the cat may have recommendation strengths in favour of lots of different behaviours, and just one behaviour, or a compatible group of behaviours perhaps, must be selected by the competition subsystem. Those same columns could also recommend a wide range of internally directed behaviours, like prolonging the activity of columns that are currently detecting their receptive fields, or releasing detections from one area to another, or indirectly activating more columns, or driving receptive field expansions. And a different type of internally directed behaviour is changing recommendation weights, what I'm calling reward behaviours. To give an example of information flow behaviours, suppose the system is looking at this scene, with a dog barking at a cat and the cat's up a tree. The top array of columns in this new diagram detects receptive fields within current sensory inputs, and these receptive fields discriminate between different types of visual objects. The bottom array detects receptive fields within groups of objects, and those fields are good for recommending different behaviours in response to this scene as a whole. One such behaviour might be calling off the dog, for example. One information flow behaviour is to limit the sensory inputs within which receptive fields will be detected to one object in the visual field, like the dog, and detect the receptive fields present in just that one object. A second information flow behaviour could then be to limit the sensory inputs being processed to a second object, say the cat, and detect receptive fields just within that object. And yet another behaviour is keep the receptive fields detected within the dog still active, but separated so that the information isn't confused. Then a third behaviour could be to detect receptive fields just within the third object, the tree, keeping receptive fields within the first two objects active, but again separate. And as we discussed earlier, separate means keeping the three sets of receptive field detections at separate phases of frequency modulation. Then, the next information flow behaviour could be to bring the three sets of outputs from the first array into the same modulation phase, so they reinforce each other, and provoke receptive field detections in the bottom array. And those more complex receptive field detections may have recommendation strengths in favour of different external behaviours in response to the group, calling off the dog, yelling at the dog, putting a leash on the dog, and so on. But those same receptive fields in the second array may also have recommendation strengths in favour of internally directed behaviours like indirect activations on the basis of past temporally correlated activity. And that could drive the activation of a secondary receptive field population. And that secondary population might contain some of the receptive fields active in the past in response to some similar scene, perhaps a squirrel being chased by a cat up a tree. So that secondary population will create in the system a vague version of that earlier experience. A novel scene with both the cat and the dog up the tree would result in too few receptive field detections in the bottom array, resulting in receptive field expansion behaviours. Now, reward behaviours, changes in recommendation strengths, have a strong effect on future system behaviours. So such changes also have to be behaviours that have to be very carefully managed. Suppose that the small boxes are a set of components corresponding with different external behaviours. Purple boxes correspond with weight change behaviours or reward behaviours. Then there are various arrays of columns that provide receptive field detections that are provided to these components. And the components interpret these inputs as recommendations in favour of their behaviour. Suppose that some receptive fields are detected in the top array, and these detections recommend the behaviours in the top row. The competition process determines the most strongly recommended behaviour and implements it. Usually it'll be some subset of the active receptive fields that provides most of the recommendation strength in favour of the accepted behaviour. Now, suppose that shortly after the accepted behaviour, receptive fields are detected in the lower array, and these detections are inputs to the reward behaviour components and are interpreted as recommendations in favour of those reward behaviours. One reward component has the largest recommendation strength, and this reward component is the one that acts on the component corresponding with the recently accepted external behaviour, and it increases the recommendation strengths that led to the acceptance of that behaviour. So the probability that the external behaviour will be accepted again in similar circumstances in the future is increased, although once again there have been no changes to the receptive fields. Now there's a problem here. How does the system know the appropriate circumstances in which to apply a reward? And furthermore, under what circumstances should the recommendation strengths in favour of reward behaviours be changed? In other words, when do you reward a reward behaviour? Especially since rewarding a reward behaviour could have an extremely strong effect on future behaviour. So rewarding a reward behaviour will have to be a behaviour. And then, of course, how do you determine when to reward the behaviour of rewarding a reward behaviour, and so on? But we'll leave discussing how a system could address this issue until a bit later. So we've concluded the importance and limitations of consequence feedback forces the architecture of a complex learning system into the two subsystems. One of these, clustering, performs condition definition and detection processes. The other, competition, performs behavioural recommendation processes. Behaviours of the system include actions directed towards the external environment, but just as important are the behaviours directed back into the system itself. Those internally directed behaviours are critical for generating sophisticated externally directed behaviours.